There, we're live. Hi.
Hello. I'm still writing my intro.
It's all good. It's all good. I just realized that they ran a giant model in preparation for Euclid, and I'm trying to understand why. Well, I
a
have audio
giant
coming from somewhere.
a giant model?
Yeah, so there's this massive simulation of the universe that was run by the Euclid Consortium. So they have comparison galaxy
Oh yeah.
models.
I actually interviewed somebody about this, so I
Okay.
know quite a bit about it. Yeah.
Okay, cool. You get to talk about that part because I just discovered that part.
Sure. Yeah. Um
Whew. I'm having the Mondays. So, for those of you wondering why we're both uh, zoned out, Fraser has been preparing to have construction humans coming
okay.
there,
Yeah, we're getting a battery system installed is the plan.
which is
So,
quite
one of
exciting.
yes, for people who have their power go out 10 times a year for sometimes a day or two. The downside of living in the countryside. So we're getting one of those backup battery systems.
Which is excellent.
Yeah, I'm quite excited. So the power will go out, or our power will never go out again. We'll have no idea that the power went out on our road. There'll be a big storm. We're like, ooh, I bet the power went out, but not for us. So
That's
yeah,
excellent.
yeah,
How
yeah.
long will the battery system be able to sustain everything?
I don't know. So we're just getting one, and then we'll
Mm-hmm.
sort of like that should take the rough edges off of it.
Mm-hmm.
So if I think that'll last us like kind of 6 to 8 hours, depends on whether we're in the middle of winter time and
Okay.
we're running our because we don't have any like everything we do is electricity, so we don't
Right.
have a fireplace, any of that. So really, it's how long can it run our heat pump? So not a power wall, but the another company's equivalent of a power wall, but just one battery pack. And then if it finds that we ran, because typically our power goes out for 4 hours or so.
Yeah.
And so if the power is out for longer than that, then the battery system will run out and then we'll have to. So I'm gonna play around with it, right? Where I like have the heat pump run at a lower energy rate or whatever, right? We'll
Yeah.
figure it out. And hopefully
Yeah.
it can run longer. I mean, the worst case has been 48 hours, and I don't think it can handle 48 hours, even if we fill our wall with battery backups. So
Yeah. At that point, you really need to have a generator or some other
yeah, and
source of
we
power.
just don't want one. Like for sure, we can get one of those like propane generators that sit
Yeah.
outside. Um, uh, so people are saying they hear us on Twitch, but they don't. Oh, it's Alan Gross is saying they don't see us.
So I know that we can be seen on YouTube because I accidentally forgot yet again to press pause, but this time didn't have my audio going into the stream, so it was
Okay,
okay.
okay,
And
okay.
so I know, I know.
Yeah.
Um,
Zappan saying give it generator two or use the leaf. No, I mean like this should be more efficient than the leaf because we'll be able to control exactly which parts of the system are tied into the backup battery. And so it'll literally just be whatever is required to keep our house from not falling apart until the power comes back
yeah,
on. So
the
we
lack
will know
of
when the power has gone out.
fireplace is what worries me for you, because like it can get
Yeah.
cold, and
Yeah, so it has happened. So our power has gone out in the middle of winter when it's minus 10,
hmm
and because we have a concrete floor, the thermal mass in the place is actually and the places like modern
oh
homes are just
yeah,
so tight. I mean, we have our 30 walls, our 40 ceiling. And so over the course of 20, I think the longest during like really cold, like minus 10 outside, we were down for 12 hours. And I think our house had lost 2 Celsius in 12 hours. So
Yeah. Our house can do that if you look at it funny, but our
yes,
house
yeah,
was
yeah, yeah,
built
yeah.
in.
Yours, yeah,
Yeah.
your house is a, is like a, I don't know, is a ventilation system,
Yes.
right?
Yes.
It's air in
Yeah,
and
it's
out.
kind of
Yeah,
wild.
yeah,
But it was built in the 1890s and
right.
has had many critters add holes to it and the windows. I don't think they're original, but they're pretty close to
Yeah,
original.
yeah.
So yeah.
Uh, Zap fencing, you have so much wood around, fireplace would seem natural. So I grew up in a rural scenario, and I was the one responsible for lighting the fireplace every day. I chopped all the firewood, I chopped all the kindling.
And
My
you never
dad,
want to do it again.
and I never want to do it again. Yeah, why would I run a fireplace? It's madness. They suck. And they produce gases that you have to breathe in. So they produce air pollution. They are, they're not. I mean, I guess it's carbon neutral, but I would rather have my wood decompose slowly, encouraging life forms to thrive. So yeah, I hate fireplaces. I hate wood stoves. I hate all that. No, I want electricity. So um, so in the short term, I mean, right now we've just got the battery backup, and then the long term, we're going to put up solar panels, and then the long term is I'm going to put in a small hydro plant on the property where in the wintertime, because like in the summertime, we have lots of sunlight. In the wintertime, we have lots of rain, and
Yeah,
the rivers start to flow around our house. We can hear them. And so I
that's
want
wild.
to run some small hydro plants that are just giving me enough electricity to run my house. And then we should be relatively self-sufficient at that point. But mostly just because I'm a nerd and I want to be able to do this kind of stuff, which is sort of, I find it so fun and fascinating. But no, no, absolutely not. I will never run a wood fireplace. Hell no, they're awful. I don't. It's funny because like we don't have a fire ring. And
Yeah.
people are like, oh, you should have a little like place you can sit out and enjoy the fire. And it's just like it sounds great on paper, but you sit out on a fire and the smoke goes in your face and the mosquitoes come out. No, thank you. So we are not that kind of people.
Yeah, and with that level of insulation, you don't need to be. So it sounds amazing. It sounds
No,
absolutely
no. I mean,
amazing.
we can sit outside if we want, or we sit inside if we want. And yeah, again, I've done, I don't know, hundreds of nights of sitting outside around a fire, trying to find a place to sit so the smoke doesn't go in your eyes. So yeah,
Bill
yeah.
Nash over on Twitch is like, Fraser puts a fire video on an iPad and basks in the glow.
Yeah, yeah, there you go. Yeah, we used to have a place in Vancouver where we had a natural gas, one of those natural gas fireplaces, and you just, press a switch and your fire comes on, and that's
Yeah.
that's that's great,
Yeah.
perfect. So I did a telescope live stream last night
Good. How did it go?
with amazing. Oh my God,
Yay.
yeah, yeah. So this is provided by Starfront, and which Bray Falls, if people are familiar, one of the best astrophotographers in the world, is running this sort of designed a telescope paradise in Texas. And so they've got like six barn-sized buildings where they've got dozens of telescopes on piers inside each one of these buildings.
Yeah.
And then they roll back the roof on the nights when they have clear skies, and they have like 95% clear skies
Yeah.
historically so far. And then you operate the telescope remotely. And so back they loved back what we did with Bray provided photographs for our book.
Yeah.
And they were big fans of the Star Party back in the day. And so they reached out and said, oh, do you want to have a telescope? I was like, yes, please. So they set up a Celestron Origin, which is the Celestron version of the Unistellar and the uh like the Vaonis, these smart scopes, right? But it's Celestron's take on this.
Uh huh.
And And it's just an astonishing piece of technology because you have this list of things. You're like, I want to see the Omega nebula, and you type it in and you can see this visualization of the telescope moving to the place. You then start imaging, and then it just starts doing however long exposures you want, just stacks them up in real time. You see
Yeah.
how the image is coming together, if you like how it's turning out. And then whenever you've had enough, you stop imaging, and then it pumps out the final image, and then you can download it and share it. And so it was just like butter. It was so smooth. I mean, I must have shared, I don't know how many pictures I shared. I guess I can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's about 15 images in, and this was me trying to learn the system in about an hour, but also explaining the technology and answering over and over again where the telescope was and what kind of telescope it is and why don't we look at Saturn and things like that. So it was yeah, it's amazing. And so now we layer it on. So like we'll have people like you come and
Yeah.
join me, and then we'll just hang out for an hour talking about space, but also imaging space while we're doing it. So and then
It,
hopefully, oh, there's all these other astronomers that are part of this Starfront. And
yeah.
so I'm sure I'll end up with dozens of them coming and hanging out and being a part of the event as well. So and then sharing their pictures. So I'm really excited about sort of the next true iteration of the virtual star party.
And we can all together be annoyed that T Corona Borealis refuses to go nova.
Yeah, but the second that it does, we'll look
You'll
at
be
it.
on it. It was
Yeah, yeah.
waiting until you had your telescope ready to use.
Yes, that's exactly it. Yeah. And then just the speed of this telescope. I
Yeah.
mean, 30-second exposures is enough for Andromeda and the Comet and
Yeah.
Hercules and all that kind of stuff. 2-minute exposures for galaxies, and then you're off and running. And I'm sure it'll be more like 5-minute exposures for things like California Nebula, Heart and Soul
Yeah.
Nebula, things like that. Um, but yeah, yeah. And then they're setting up a second telescope for planetary.
Oh,
So a
wow.
completely separate creature that will
Yeah.
have a
Yeah.
different focal length and be designed to show, because you'll be like, oh, can we see Saturn? I'm like, you want to see Saturn? No
Right.
problem.
Right. No, you do need
It's
that totally different focal
yeah,
length.
yeah, yeah. And so I took a picture of Saturn, and then we blew it up and zoom, and it was just this horrible little blob of pixels in the middle of this cavernous space because the field of view is so wide,
Right.
and these planets are actually really small objects, you know. So it's a totally different telescope setup. But eventually, within a couple of weeks, we'll have both. We'll have
That's
the
awesome.
wide field origin and the narrow field um, planetary scope, and then we can just switch back and forth as we're looking at stuff. So
That's
yeah,
so
yeah,
cool.
it's like this is gonna work. It's gonna fulfill all of our telescope dreams at this point. So,
That's
and
very cool.
huge thanks to Starfront for just like
Yeah.
giving me access to this telescope. And like, obviously, they're gonna hopefully bring on new customers,
Well,
but
they sold out those first few barns so fast. I am not worried
yes,
about that.
yeah,
It
no, I
was
can just imagine
amazing to
you'll.
watch.
Yeah, eventually you'll just see this enormous landscape that goes on forever, just filled with telescopes and
Central
barns.
Texas.
Yeah, yeah, it's wide open spaces.
It's awesome.
All right, let's do our job.
Okay. I feel like I'm going to sneeze at some point, but it's also not like, you know, that I might sneeze feeling? I have
Hmm.
that and I hate it.
Yep.
I'm
Well,
dealing with allergies.
so whenever you do, just
Don't,
give yourself some time.
yeah,
Rich can
he can
edit that
fix
out.
anything.
Exactly.
All
Yeah.
right, I'm pressing record. I am pressing record. We are
All right.
recording in all the places.
Astronomy Cast, episode 732, Euclid. Welcome to Astronomy Cast, our week. Should I say the Euclid mission? Because then
Yeah,
Euclid Space Telescope. Yeah, all right, we'll
yeah,
do that.
yeah.
Okay. Astronomy Cast, episode 732, the Euclid mission. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain. I'm the publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. I'm not sure how. It is grant writing season. It is a presidential election year.
Yep.
And the leaves, oh my goodness, they need raked. I am in denial of so many things. How are you, Fraser? That's the real question.
I'm good. And I talked about this before the show, but we are getting back with the virtual star party. We've got just an incredible generous offer from an organization called Starfront. They host telescope co-location down in Texas, and they have set aside a telescope just for me, just for the star parties. And so last night I did my first test run with this telescope, and it's amazing. It's a Celestron Origin, which is a smart scope, and so it goes super fast. It knows exactly what it's looking at. It images in real time, so you can watch as the image builds. And I can't believe how smooth this went. Normally these things are a technological nightmare, but last night when I did this first test run, it was incredible. And so hopefully over the coming weeks and months, we will just do more and more of these, make them more interesting, packed with scientists and special guests and more people bringing telescopes to the party. And we can look at different objects and different kinds of telescopes. We can look at planetary stuff versus deep sky stuff. And, I really hope that we'll make this just really fun celebration of amateur astronomy that we can just conduct on an ongoing basis, as we've tried to do over and over again, right, since 2012. So it really felt like now it's just minor tweaks and fixes to make this my dream show. So if you haven't checked it out, check out the sample of it. But chances are you'll see me live with this telescope very often in the coming weeks and months.
I am. This is the news. I was here to hear. I was here to hear.
Yeah, totally. So ESA's Euclid mission launched last year with the task of mapping the universe in thrilling 3D. They've dropped their first preliminary data release containing just 1% of the universe. And so it's a good time to talk about it. And we'll talk about it in a second, but it is time for a break. And we're back. All right, Pamela. So, we haven't gotten the full first data release from Euclid. I think we're waiting till 2025 for that first drop. But we got enough that I think this falls into the Pamela's willing to talk about, willing to acknowledge the existence of a mission zone. And I'm so excited because I am just stoked on this mission. So what is Euclid?
Euclid is one of the punniest named missions ever that is designed to, over the course of 6 years, observe roughly a third of the sky. They are specifically looking at parts of the sky that aren't interrupted by the disk of the Milky Way or other galactic pollution. And they are measuring all the shapes of galaxies out to a distance of about 10 billion light years and using this information to map out the distribution of dark matter and to measure the evolution of large-scale structure over time.
And so let's talk about sort of its location and position and all that kind of stuff. So where is it?
It is out at L2, the place where we love to stick space telescopes. It's on that line that goes Sun, Earth, telescopes, where it's gravitationally balanced and hangs out as we go around the sun far enough away that it's in constant communication and doesn't have to deal with a lot of issues from the planet Earth, and it's not going around and around us, and it just makes everything easier to do science.
Right. Like it puts the Earth, the sun, and the moon all in one tidy spot in the sky.
Yeah.
And so then it can point in the opposite direction and view whatever it wants, and yet can be pointing its antenna back at Earth and have a continuous view back to the planet. But it doesn't need that heat.
No, it
block
doesn't
in
have
the way that Webb does.
No, it's living out there simply because that is a very good place to put telescopes, and it actually worked out more beneficially than we could have known before it took off. This is a telescope that getting from idea to where it belongs was a long and storied journey, because it was originally put together as a medium class mission idea while ESA and Roscosmos were still working together. It was originally supposed to be a Roscosmos launch. They then had to partway through construction go, oh, nope, not going to do that.
Right.
Rejigger things. There's been a shortage of Arians, and so they ended up launching on a Falcon 9. They take their 30-day journey, get out where they belong in the vicinity of the Earth-Moon system, and they found on their images this blotch of light that was not intended to be there. And it turned out they actually had a light leak in the side of their telescope.
Oh, wow.
And so they had to figure out, how do we uh, change the way we're doing things so that sunlight never directly pours in through the side of the telescope. And it was no big deal. They totally did it. But it was just one of these things of, okay, I'm glad it is where it is, because there are fewer sources of light to worry about. Okay,
Yeah.
we're good.
There was another challenge that came up. I don't know if you were watching this, but they were getting condensation inside the optical elements of the telescope. And this is actually pretty common. Like, all telescopes have this situation, because they, even though you try and build it in the driest environment that you can, you're still going to get some water vapor from the Earth's atmosphere going into it. And then when you're out in space, in the vacuum of space, then this water vapor evaporates, condenses onto various parts of the optics, and starts to decrease the light gathering capability of the spacecraft. And so what's fascinating about this is that they were ready for this. They knew that this was going to be a problem. They'd seen this happen on other missions. And so they had heaters built inside their optical pipeline, so that they're able to run the heaters sequentially at the right times and be able to vent out all of that additional water vapor once it was out in space. And they were able to make that condensation go away and increase the sensitivity of the optics by a couple of percent, which is sort of incredible. And I think a lot of other telescope manufacturers will then think about that same strategy when they build their own missions.
And I have to admit, now that you're telling us about it, I had blocked that memory completely.
Yeah.
And yeah, this is just a system that came together, kind of hung out without doing a whole lot of press, and then whoop, here's the most magnificent image of galaxies ever produced.
Yep.
Hi, what do you think of this? And
all right, we're going to get to that.
Yeah.
But I want to talk about its goals first.
Okay.
And before we even do that, we should stop for another break.
All right.
And we're back. All right. So what are the science goals of Euclid? What is the purpose of this mission?
Okay. So goal 1 is, it is going to map out the shape of galaxies out to 10 billion light years away.
Mm-hmm. Yeah.
Now, the reason they are doing this is not just because it's cool to know the morphologies of galaxies. That's not actually what they're trying to do. It turns out that dark matter has this wonderful little habit of bending light. It still has gravity. You can't see it, but we measure everything about it through its gravity. And when you have a blob of dark matter between us and a distant galaxy, it will ever so slightly distort that galaxy. And when you look at a large enough sample of galaxies on the sky, you can see, well, this pocket of galaxies should all average out, when you look at all of them, to being a circle. That's just on the sky. They should all look like circles. And then it turns out they're actually a teardrop. Then you look over somewhere far away on the sky at another blob of galaxies, and they also should all average out to being a circle, but now they look like an amoeba from your 5th grade science class. And these distortions that we're seeing are all due to the dark matter that we don't see between us and these walls of galaxies distorting what we see. And one of the most amazing things is, if we look at a wall of galaxies that are all at a redshift of, say, a half, that is going to allow us to map the dark matter between us and that. We then look at a bunch of galaxies at a redshift of 0.75. they're going to have a slightly different distortion that's
Mm.
due to the nearby dark matter and the further away. And the further and further we look in Redshift, the more dark matter has a chance to distort those galaxies. But because we have this distribution of galaxies all the way out, we can start to uncouple all of this and map in 3 dimensions what the dark matter is doing to the observed morphologies of galaxies.
Right, right. And so by measuring, like really by just looking at the shape of
Yeah.
every galaxy that you can see, as you say, out to that sort of time horizon of 10 billion years,
Yeah.
then you're able to then, it's, I don't know, like the example would be like lying at the bottom of a pool of water and looking up at the trees above you and measuring how the shape of the trees look. That tells you about the water that's in between you and the trees. And so in this case, you are, by looking at the various blobs that the galaxies have become, you can calculate how much dark matter is in between you and that galaxy, where the concentrations are to a level of accuracy that we've never had before. I mean, Hubble does this, Webb does this, but this is a telescope that's only job really is, well, I guess half of its job. It has another
Yes.
half. We'll talk about it in a second, but half of its job is to measure, really allow astronomers to reverse engineer the quantities and locations of dark matter, this thing that is invisible, and yet because we can see its gravity, we can
Map
see the
out what it's
invisible.
doing. And
Yeah,
this was
yeah,
done most notably early on in Astronomy Cast by the Cosmos survey. And I know we both had oh my goodness, that model was so amazing,
yeah,
glowing about how awesome it was. And to go in the course of the life of this podcast from a pencil beam survey, able to do this for this small cylinder through the universe, or I guess expanding wedge through the universe, to now seeing a spacecraft that's going to do this over 6 years, just 6 years for
yeah,
a third of the sky, is revolutionary.
yeah, yeah. All right, so that's half of its job,
Yes.
which literally it has one instrument, a visible light telescope that is taking these pictures of the galaxies and their weird wonky shapes.
Yeah.
So it also has an infrared instrument on board. What's that for?
Well, it has the spectrograph. And so it's this the spectrograph is the more key part of this. It is measuring the redshift of all of these galaxies, which tells us their relative locations in the sky. And it's mapping out the changing large-scale structure over the evolution of the universe. And from that 10 billion light years away, a z of about 2 that it's starting up until now, somewhere in that window is where dark energy began to dominate the expansion of the universe, where we went from things are expanding away but getting pulled on by gravity. It's the Big Bang effect to no dark energy is now pushing us and accelerating us apart. We're still
So
trying to come to terms with that. Go ahead.
right. So I want to sort of better understand how this is doing that. So like you've got this spectrograph
Yeah.
on the spacecraft. It's taking a picture of a galaxy. How does it tell us the redshift of that galaxy? And so kind of like to tell us how far away, because the same galaxy, we could be seeing it close up, it's just smaller, or farther away, it's just bigger. How do we place that galaxy in that sort of distance slice?
So, lucky for us, atoms have these fingerprints of spacings of their atomic lines that are related directly to what is sitting in their core, how many protons, how many neutrons. And these fingerprints are the spacings between the absorption or emission lines, depending on the thermodynamics of wherever the atoms are located. And when we look at the spectrum of anything, we say, okay, I see these sets of lines, and use pattern matching software, or in the case of some brilliant scientist, brains, to say, oh, this looks like the hydrogen, calcium, and you can just
Mm,
see what the sets of lines that match these must be. And this is how originally we figured out quasars were at huge distances because their lines didn't match nearby stars. And it was a researcher who's used to thinking about the more distant universe that looked at it and went, oh, those are redshifted lines from something at a great distance that, because of the expansion in the universe, has carried what would normally be ultraviolet lines into the optical, what would normally be
right.
optical lines into the infrared. Or if it's really far away, like ultraviolet lines into the infrared. That can be a thing.
Right. So we look at a galaxy,
Yes.
we use the spectroscope to measure the absorption lines in that galaxy, and we see, say,
Yes.
3 lines in a row with little gaps in between, and we're like, oh, that's calcium, magnesium, and carbon dioxide. We could see their presence in this very recognizable pattern. So how do we get the distance of that galaxy once we have recognized that fingerprint?
So there are this is where it's still an inexact science because we have to get at it off of other things like supernovae. So going back to Hubble, when we look out at things that we know the distance to due to variable stars or now today other means of standard candles, we say, okay, because I know this object has brightness 10 and I measure it as having I know it has luminosity 10 and I measure it to have a brightness of 16. And because we're astronomers, 16 is way fainter than 10.
Right.
That amount that it appears to have faded is directly related to its distance. It's the square of the distance.
But you're also measuring those absorption lines at a different location when than if the galaxy was right beside us, right? Like they've been redshifted away.
So we have to do two different measurements. So
Yeah.
if the universe wasn't expanding, then those lines would be at the exact same wavelengths if the galaxy was 2 billion light years away as it would be if it was right next to us. But what Hubble discovered is if you make a plot of what is the distance to something based on how bright it appears and knowing how luminous it should be, and you look at the chemical signature of its atoms and see how much they have been shifted to the red or the blue, something that is shifted towards the blue, we know, and we can do lab experiments with this, is moving towards us. Something shifted to the red is moving away from us. And it turns out there's a direct relationship between how much something is shifted to the red and
Right.
how much fainter it appears because of its distance. This is Hubble's law. It is the linear relationship, we thought, between velocity and change in brightness.
Right.
Except then in 1998, the supernova people were like, okay, we've got some bad news for you.
Right.
The math is so much harder than any of us ever wanted it to be because it turns out that relationship isn't actually linear and it isn't what we had thought, which was things would be slowing down over time. No, our universe is expanding at an accelerating rate, which no one expected. So we made up
Right.
words because astronomers do that. And we called whatever is causing the universe to expand apart at an accelerating rate dark energy.
Mm.
I can't tell you
Yeah.
why. We just did.
No, and I think we all regret the name, but
We
it
do.
stuck.
Yes.
Um, and so that's the part that's kind of interesting. Like one of the big unsolved questions in astronomy and cosmology is the amount of dark energy that's entering the universe a constant?
Yeah.
And if it changes over time, what are the implications for the far future of the universe? And the hint that there might be something weird going on is this Hubble tension. And we've done whole episodes
Yeah.
about this, but the gist that you seem to measure the expansion rate of the universe at different times, and it doesn't match up to standard expansion plus standard amounts of dark energy. Like there's something weird going on at some point in this process. And there has never been an instrument that is more appropriate for making these exact measurements
Well,
than Euclid. It is the
and
machine.
Euclid is getting at this in an interesting way where it is saying, okay, so we know that there were these things called baryon acoustic waves in the early universe that caused the initial distribution of matter in our universe to not actually be smooth. There were places that were a little denser, there were places that were a little less dense, more empty. And over time, those regions that were less dense got emptied out as material was pulled out of them and pulled into the more dense regions. And this formed the large scale structure of our universe. And the rate at which that large scale structure formed is one of the things Euclid is directly measuring. It's
Mm.
looking to see what is the evolving signature of the baryon acoustic oscillations on the structure of our universe from what we see in the cosmic microwave background radiation to what we see in the distribution of galaxies changing over time.
Yeah, yeah. Um, and so once it's performed this survey and done this, as you mentioned, this 1/3 of the entire universe, we will have the position and composition of billions of objects across the universe, telling us with incredible accuracy how much dark matter there is and where it's located, and then what role dark energy has played throughout throughout the entire evolution of the universe as far back as can be seen as 10 billion years. So we're going to talk about the sneak preview that dropped last week in a second, but it's time for another break. And we're back. So ESA dropped this data release, but
Yeah.
not a true data release. This was just a sneak
No.
preview last week. What was in it?
1% of the sky.
Right.
I
How
just,
much?
I just, it's like one of the largest single images ever released.
Yeah.
Single image is really the wrong way to put it. One of the largest zoomable contiguous mosaics of images ever released. It is 208 gigapixels and contains 260 observations from March 25th to April 8th. So 208 gigapixels is like a couple weeks of data.
Right. There's, what is it, 100 million objects in the pictures?
And there you can see this, what we call the cirrus of the Milky Way, which is something I have never seen visualized this clearly. As someone who did galaxy surveys once upon a time, we were forever looking up in tables of information what was the amount of stuff between us and the outer edge of our galaxy that would be affecting
Right.
the brightness we measure of those galaxies. This was a coefficient you just looked up and then you adjusted all of your photometry by it. But I had never seen the
Right.
clouds of gas and dust, the cirrus
Oh,
of our galaxy. And it's just hanging out, shining bright in these extremely sensitive, extremely high resolution images. And it's
oh,
just
that's
sort of
amazing.
like,
Like imagine you're, I don't know, you're trying to paint a landscape that is very foggy,
yeah,
and the fog is kind of rolling around, but the fog doesn't move. And so you've got a book that you have to look up where you go, if you're looking at the car on Third Street, then just remember that that the colors are shifted a little bit and that it's more of a limey green than it is a
yeah,
green color, whatever, right? And you would
exactly.
have to look these up. You'd be like, I'm looking at this galaxy. What is the amount of possible Milky Way related dust that's between me and that object? Okay, here's the number. Okay,
Yeah.
modify my photometer accordingly. But you're exactly right. When you look at these pictures, you're seeing these swirls of blue gas and dust, which is just part of the Milky Way swirling around. And you can see some objects that are not affected by it at all, in other cases where they really are affected by it. Just absolutely incredible picture.
Only 32 more percent to go. It's really
Right.
wild. And the thing that I'm sure I read about long ago and then went, I do not need to worry about this right now, and promptly forgot was there was one of the largest cosmological models ever run to simulate what should the distribution of galaxies look like in the Euclid survey. And then you told me before we went live, this is something you've done interviews on. And this man that's here does way better interviews than I can dream of doing. So just go watch his interviews. So what did you learn about this model I totally forgot about?
Essentially what they did was they took the like one of the big simulations they've made. I think it was the I forget the name of it, the Illustris. Anyway, researchers have been making these gigantic simulations of chunks of universe. And so what they did was they took one of these chunks of the universe and then they simulated what that would look like as it fell on the sensors of Euclid, and specifically, but also, sort of considering other instruments as well, and then provided the outcome to the scientists and said, when you look at this Euclid data, this is how it's going to appear in the databases that you're going to be downloading. And so double check to make sure that you're happy with what it is that we're observing, and then make sure that that you can use the output data and then use that to kind of calibrate back. And that was the thing they provided before what they provided last week. And so last week they provided the real data. And now it's a matter of checking, comparing the actual results from Euclid compared to what the simulations had said you were going to be expecting. And there's just it's kind of incredible that people are trying to simulate the universe, but also one of the really interesting downstream applications of this is that you can give astronomers sample data that is very accurate to what the final instrument is going to be able to produce.
And this also provides a check on our physics, because if it turns out that the strength of dark energy is varying more or less, well, not less, but more than we thought, we will see it as a discrepancy in the rate at which large-scale structure forms. And so we're going to be able to compare these model results with the reality of our universe and say, yes, it looks like we actually got this section of physics correct. We have some errors here. We need to tweak this over here. And it's getting to the point that in order to understand, if we understand the universe, we have to run complex gazillion particle simulations to compare against reality, because we're that in the weeds nowadays, and it's kind of amazing.
Yeah, it is amazing. So when should we expect to see more? When should we see the real science coming from Euclid?
It depends on what you're looking for, but I suspect that after every 12 months of data, we're going to start to see a little bit more science and a little bit more science. And as always, the final results will probably come 2 or 3 years after the survey is complete. And what I'm waiting to see is just how long do they keep this mission going? How long does this telescope work? And do we start taking on more of the sky?
It's funny.
Mission.
I'm trying to line up an interview with someone from the Euclid team, and I know the questions could be, you say 6 years, you say 1/3 of the sky, but come on, right? It's the whole sky, right? Right?
Well, not the whole. There's no reason to do the disk of the Milky Way. We can avoid the disk of the Milky Way.
Sure.
That's different science.
But there's value in taking pictures of the disk of the Milky Way too. But still, I mean, that's the part that I think would be really interesting. But still, hopefully over the coming years, we will come back again and again to talk about what we've learned from Gaia in the way we've talked about what we've learned from Hubble and, from Gaia, from Euclid. Yeah, sorry. In a couple of years, we'll come back and look at what we've learned from Euclid in the way we've talked about the updates from JWST and Hubble and Gaia and other missions out there. So yeah, this is the beginning of what is going to be a really entertaining story for the next decade. So I'm looking forward to it. Thanks, Pamela.
Thank you, Fraser. And thank you to everyone out there who is part of our Patreon community. We can't thank all of you by name, but we do take on a group of the $10 a month and up patrons every week. If you want to hear me say your name, I'm going to be running the November names at the end of the week. So join the Patreon. This week, I would like to specifically thank Andrew Stevens, Astro Bob, Astro Sets, Brenda, Brian Cagle, Brian Kelby, Bruce Amazine, Daniel Loosely, David Disastrina, Don Mundus, Elliot Walker, Father Prax, Glenn McDavid, Greg Davis, Gregory Singleton, Hal McKinney, Jeff Collins, Jeff Wilson, Jeremy Kerwin, Joanne Mulvey, Joe Holstein, John Thays, Jonathan Poe, Jordan Turner, J.P. Sullivan, Klum Badrov Loves Science, Christian Maggersholt, Kansaya Penflenko, Larry Zote, Lee Harborn, New Zealand, Mark Stephen Raznek, Mike Heisdy, Nyla, Noah Albertson, Paul L. Hayden, Robbie the Dog with the Dot, Robert Cordova, Robert Plasma, Scone, Scott Bieber, Sean Matz, Stephen Veit, the Air Major, the Big Squish Squash, the Lonely Sand Person, Thomas Gazeta, Time Lord Iro, Tricor, Will Hamilton, and Zero Chill. Thank you all so much.
Thanks, everyone, and we'll see you next week.
Bye-bye.
And then I saved.
Yes, and I breathed.
Were we going to talk about Euclid the person next week?
Yes.
Okay,
Yes.
awesome.
Let's show the ancients some love for a change.
Yeah.
I just love that they named and I'll go into this more next week, a mission that is measuring the geometry of the universe after the OG geometrist.
Yes. Yeah, I mean, it
It's
feels
on the
like
nose.
Yeah. Like you know, when you think about you could have gone for people who figured out dark matter. You could have named it after people who figured out spectroscopy. You could have figured out people who worked on dark energy, but nope, you went all the way back to the most fundamental part of this process, which is just measuring triangles.
Yes.
Thanks, Euclid.
Yes. I love it.
It's awesome.
And
I
they
100% agree with you.
They ran no risk of accidentally finding out later that they had named it after someone that it turned out was
problematic.
Yes. So
well, I'm sure Euclid was problematic. It's just that, you know, people have been wrestling with his, you know, did Euclid own slaves? Like, who knows how awful
Right.
Euclid was, right? But
Yeah.
people have been come to grips with Euclid for
centuries. Millennia.
yeah, for centuries. Yeah. At a certain point, there's, I don't know, statute of limitations. I don't know though, right? Like, if, you know, how awful can a person be where you
Well.
have to sort of go, well, you know, we're going to cancel him from, you know, do we cancel Genghis Khan? I think so.
I think Genghis Khan was canceled long ago.
Yeah, possibly. All right, so now we've got another 9 minutes, so let's deal with some questions that people have. Doran Smillian asks, if the galaxies rotate and we see the edge on or face on, then the chemical line can cause more or less curves around that redshift. So is that true?
Wait,
Does
say
the
that again?
orientation of the galaxy where parts of it are rotating change our measurement of the redshift of the galaxy, whether it's face on or edge on?
It just broadens the lines different amounts. That's all. So
and in fact, we can measure, if you get enough resolution on the galaxy, you can measure the rotation speed purely by the redshift of the two halves of the galaxy.
yeah,
right?
if it's edge on, you can measure its rotation. If it's face on, you don't see that same broadening of the lines. You see some broadening because there's always stars in squirrely orbits. But yeah, it's just how much the lines broaden.
Yeah. Justin asks, if gravitational waves move at the speed of light, isn't there a way that they can do spectroscopy on them?
Not so much. So the issue is gravitational waves are the frequency of the waves is due to the spin down of the objects and the masses of the objects going into it. So you're not getting a variety of wavelengths simultaneously that would allow you to have a spectrum.
Right. I mean, when you think about how that spectroscopy is happening, you're literally, if you light a car on fire, and then you take the light that's coming from that car fire and you spread it out, you're going to get the chemical fingerprints of all of the stuff that the car is made out of showing up in that light. You're like, oh, that car's got titanium in it, that car's got aluminum in it, and so on. But a gravitational wave, as you say, you would need to have a wobble on the spin down or something so really you just get the as the wave flows by, you're like, oh, two perfectly spherical
Yeah.
black holes just merged. Oh, a a supernova went off, and you just get that measurement. It's more like sound, I guess, right? Like
Yeah.
we don't do spectroscopy on sound,
Yeah.
do we?
Well, I mean, yes, but it's to measure what combination of instruments it is, because it's literally different sound waves. Like if you're looking at the sound coming off of a synthesizer that's trying to be a flute versus an actual flute,
Yeah.
you can see the overtones and stuff, but that is totally different. It is
Right.
completely
Yeah.
different.
Yeah.
So yeah.
Right. Awesome Avengers faithful canine sidekick asks, what is the consensus on the existence of other universes, and is there any evidence that may suggest that there are other universes?
I want to say consensus is edging towards we live in a multiverse. But beyond that, I'm not too comfortable saying we have like strong consensus on anything other than
Hmm.
it's probably a random distribution of initial conditions.
I mean, there is no observational evidence
Yeah,
of multiverse. So there is no experiment, no observation that has ever said, oh, yeah, there's the other universe over there, or we can contact it, or we can jiggle particles, or whatever, right? But I think there's kind of like two things. Like, one is that there's the Copenhagen interpretation of quantum mechanics, and
right.
then there is the
Fine tuning,
multiple,
the
yeah,
multi-use,
the multiple universe one, which is that
multi-universe. Yeah.
an easy explanation for how the way quantum mechanics turns out, how is that you just have that the universe branches off into multiple universes every time a decision gets made. That perfectly explains the weird behavior of quantum mechanics, but it's a lot to
Yeah.
take in to go, oh yeah, of course. The answer for this is that an entirely new universe spawns out and splits off from this point and is a real physical thing that exists. But the
So
other one that is a lot more satisfying is the sort of implications of inflation.
yeah,
And
the
so
bubble
when you think
universe
about,
theory.
yeah, that inflation seems to explain the universe that we have today. It answers a lot of the questions for the Big Bang, but the if you are going to have inflation, and there is like indirect evidence that maybe inflation is true, and so but one of the implications of inflation is that it is ongoing across the universe. It's stopped at different points, and so you're going to have, as you say, these bubble universes that are still running under inflation, or the inflation stopped yesterday, or the inflation stopped before the inflation started in our universe. And so each one of those could essentially be considered its own non-overlapping universe as well.
Larry Susskind wrote a really good book on this, and I can't remember its name. And
Mhm.
and just to step backwards and say very, very specifically, there are two different ways that are not mutually exclusive to get at a multiverse. One is through quantum mechanics, where every decision splits the universe. The other is that there is a background quantum foam out of which universes can emerge, and those universes in turn can split apart from one another. So
Yeah.
you can have one
And
universe that has another universe bubble off of it like the arm of a saguaro cacti.
there's a great podcast from Sean Carroll, who,
Yeah.
like, you should listen to his podcast anyway.
Yeah.
He does these great interviews and does these great question shows that he does, but he does these solo episodes, and he did one where he sort of defined every possible idea of the multiverse that has been thought through so far, and you'd be kind of amazed because there's not just these ideas that we mentioned here, but if the universe is infinite, then you get repeating versions of the observable universe. Is that a multiverse, right? And you don't need to invoke any new physics. You just literally just need to have an infinite universe to now have multiple versions of the observable universe, where there's going to be people in, X quadrillion light years away are making a podcast exactly the same as the one we're having today. That you can have multiverses in terms of time, where you just, like, if you play forward the universe for 10 to the power of 10 to the power of 100 years, then things that are incredibly remote and random from happening will happen an infinite number of times. And some of those infinite number of times might be an entirely new universe popping out of nowhere, or the matter in our universe reconfiguring in a location where you get another version of the universe. And so there's like 20 different ways you can imagine a multiverse existing with higher or lower levels. Like literally, if you say the universe is infinite, then the multiverse is guaranteed, right?
Yeah.
And if the universe is infinite in time, then again, a different version of the multiverse is all but guaranteed. So
And
yeah, it's
and
a fun idea to think about.
I misspoke. It's Leonard Susskind. Lawrence Susskind does economics. It's
Right.
Leonard Susskind. And the book I was thinking of is The Cosmic Landscape. He also wrote Black Hole War, which is another
Yep.
excellent book. Basically, he's a cosmologist who can really write. So highly
Yes.
recommend.
Yeah. Yeah. And, and sort of taking some of those, it is kind of amazing now as I read various papers coming out from different researchers, and you sort of see them wrestling and struggling with these ideas. And then later on, someone like Leonard Susskind comes along and just goes, okay, let's let regular people understand the
Yeah.
really interesting ideas that people are working on. So, yeah, it's a fascinating process. Last question. Marina R asks, what about dark matter? Is there any approach to its understanding?
Um,
Did you watch the episode we just gave?
so I think the big issue right now is I'm going to assume that you mean what is dark matter.
What is it? Yes.
Yeah. So people are chasing several different paths. One is microscopic black holes, one is axions, one is sterile neutrinos, one is we don't actually understand what gravity is, and there's an additional term. There are people saying there's a fifth force.
Hmm.
Um, I don't I don't ascribe to the fifth force people, but I'm willing to say it is a mix of all the other things potentially. There could be, and there's no reason to think that there aren't microscopic black holes that I forget what it is. I figured it out the other day. It's something like anything bigger than 300 tons, which is still smaller than a carbon atom, is big enough to have not yet evaporated from
Right.
Hawking radiation. So it's possible that there are primordial microscopic black holes smaller than atoms kicking around, being a form of dark matter. It's possible there are axions kicking around being dark matter. It's very likely,
Yeah.
I think, that some fraction is going to be neutrinos of one kind or another.
It, it,
Yeah,
it's totally interesting when you talk to dark matter researchers, they say exactly what you just said,
yeah,
which is as with the search for regular missing amounts of baryonic matter, it turned out that it was clouds here and
yeah,
gas there and rogue planets here and so on. And very likely they're expecting that dark matter won't just be a thing.
yeah.
It will turn out that it is primordial black holes, it is axions, sterile neutrinos, massive objects that we don't see, and so on and so forth. And so but and that's why we have things like Euclid's job is to at least just map out where it all is and what quantities. And by seeing how much it is and where it exists and how it interacts with regular matter, that allows you to put in constraints that you can start rejecting certain ideas.
And how it interacts with itself is another part of
Yeah.
that.
Yep.
Yeah. So we live in interesting times. I don't know about you, Fraser, but I'm starting to hit the point of like figuring out how old I will be when different projects get finished and being like, oh, shoot, I'm a Gen Xer. I didn't think I was going to live very long. I need to live long enough to see these results.
Yeah,
And
I need to see
yeah,
Titan Dragonfly. I need to see
yeah,
I need to see the solar gravitational lens. I need to see the superconducting super collider, or whatever comes
That
next. I want
no,
to see the
that's not
outcomes
getting
of. I know, I know.
built.
Well, whatever comes after the
Whatever.
LHC.
Yeah,
I need to see
exactly.
Lisa and so on. All right, we've reached the end of our hour.
Oh,
So
dang. Yes,
thank you,
we
everyone,
have.
for hanging out with us. Thank you to Rich and all the rest who will have to deal with our nonsense. I know I put one edit right in there that you're going to have to catch. Thanks, Pamela, for picking this topic, which is like one of my, every time you throw me a bone and we talk about a mission, I'm excited. So
This one's
thank you.
cool. And thank
Awesome.
you. And thank you to your construction humans who aren't coming until later today.
Yep, they'll be here now in about half an hour, so the
Okay.
timing is perfect. And then they're going to shut off my power while they
Jeez.
hook this thing up. So,
Good luck.
all right, thanks everyone, and we'll see you all next week.
Okay. Bye-bye, everyone.